Thank you. Yeah. Yeah, no, I only turned it on because somebody wanted to see it on. No, you're fine. Okay, so just so you guys know, kind of going into this chapter, what is exponential and logarithmic functions? Like, what are they? The button on your calculator, I'm sure you've seen it, says log, right? L-O-G, log. That button is used, that's logarithms, to find an exponent. You guys, we've been dealing with exponents a ton, right? We've had fractions for exponents, like we've been working back and forth. We're looking at, if I would ask you 2 to what power equals 6,004? Other than a guessing game, how would you figure that out? It's where the logs come in. Now, granted, you don't know how to use them yet, and I will teach that to you, but that's what logs are for. They help you to solve for exponents. Okay? So for the first 2 sections, I'm going to actually do both of them together today. We're looking at exponential models and then the properties of exponential functions. Some of this I may kind of jump and skip through periodically throughout this set of notes. So those of you who work ahead, don't go too far. All right, so first, what is an exponential function? Just remember, f of x also stands for y. It's just a name, right? It's Frank. A times b to the x power, where a is not 0, because if a was 0, what would this whole thing equal? 0, so then it doesn't really matter. B is greater than 0, and b is not equal to 1, because 1 to any power is just 1, so that isn't any fun. All right, and x, the exponent, is any real number possible. So in other words, I'm taking a number and I'm multiplying by another number that has an exponent. That's basically all I'm doing. All right, that is the most basic form of it. We're going to look at it in some other formulas today too, where it's a little more complex than that. So we're going to graph first, so you can kind of see what this graph looks like. So let's kind of do this by hand, just so you can kind of play with the numbers a little bit. Typically, when we plot points, I lost my thing here. Typically, when we plot points, what numbers do we throw into a table? Just 0? -2, -1, 0, 1, 2. Right? We like to look at both sides, kind of see in the negatives what's it doing and the positives what's it doing. All right, so if I plug in -2, so grab your calculator, type in half times 4 to the -2 power. Fractions is the green button, and then y equals, which is 2 buttons above it, and hit equals. You could do that too. All right. So we're doing half times 4. I'm plugging in -2 as the exponent. What do we get? 1/32? If you typed it in as a fraction, you should have gotten an answer as a fraction. So -2, where's 1/32? Is it really big or is it really small? It's really small. It's really close kind of to 0, right? It's not real big. So -2, and then I'm just barely kind of off my axis. I'm not real exact up here on my board, but you know what I mean? It's just kind of barely off that. Hit the math button. Should be like a little arrow to fraction option. So my dot looks like it's on there. I don't want it to look on there. So roughly in there. What happens when I plug in a -1? What do we get? 1/8. Is that bigger or smaller than 1/32? Is 1/8 bigger or smaller? Bigger. It's bigger. Okay, think about it. If I had a pie and I cut it into 32 pieces and I get 1. If I have a pie and I cut it into 8 pieces and I get 1. Where do I get the bigger slice of pie? 1 out of 8. So -1, 1 out of 8. All right? What if I plug in a 0? It's going to be half. So guys, think about how we got half here. Somebody, like Taylor was like, isn't it 0? 4 to the 0 power is what? Who did I make disappear in this class when we talked about this? Dakota? Did I make you disappear? Yeah, right. Poof, gone, right? Because it's actually just 1. Anything 0 power is 1, but you're actually gone. So then 1 times half is just half. So 0, half. So what is it doing so far? It's very slowly getting bigger, right? It's very slowly going up. What if I plug in a 1? What do you get? 2. All right. Well, that jumped a lot. What if I plug in a 2? 8. That got real big, right? 2, 8. Look at that thing. Is that cool? So what's going to happen is this gets really close to the x-axis and it shoots upwards. Will it ever drop below the x-axis? It will not. It gets closer and closer and closer and closer to it, but it never actually will touch it or get below it. Yeah, it gets real high. Like if you look at it this way, it's going to shoot up. Could it start? Yes. So he's asking, could it start up here and drop down this way? Yeah. Nope. It's either going to shoot up like this or it's going to come up and go down this way for what we're dealing with today. Could you get graphs to do that? Yes, but not this one. Yeah. I went back 2, and then up just 1 out of 30. What's 1 divided by 32? So 0.03 is just barely above 0. So it's just barely up. It's barely up. That's really small. If I went like -3, -4, -5, it's going to get even teeny tinier closer to 0, but it's never going to actually be 0. Yeah, maybe 3%. All right. I'm going to kind of bypass this page. Let's look at radioactive decay. I bypassed a slide. Moving on. The reason we're looking at radioactive decay, because this is an exponential function. Take a look at this, guys. It's 10. There's my A. Half is my B. That's my number. And then I have some exponent. Right? That's the very first thing we looked at was just a general form. A times B to the x power. There's my A, my B, x power. So it's in that same form. So in 1986, a nuclear reactor accident occurred in Chernobyl, what was then the Soviet Union. The explosion spread highly toxic radioactive chemicals such as plutonium over hundreds of square miles, and the government evacuated the city and the surrounding area. To see why the city is now uninhabited, this is an actual true thing that happened, we're going to consider this model, which represents the amount of plutonium that remains from an initial amount of 10 pounds after T years. How much plutonium still remains there today? So this formula talks about the half-life of chemicals. If you guys have learned any of that in your science classes, half-lives. So this happened in 1986. How many years has it been? Oh, there have been a lot. How many actual number of years has it been? 30-something? It's been 32 years. Okay? Yeah, just 2018 minus 1986. Well, it's been 32 years. Yeah. So in order to figure out how much is left, we can use this formula and just plug in for T 32, because it's been 32 years. So go ahead and type that equation in for me. So if you're using the graphing calculators, it's pretty easy. Just type in 10 parentheses, half, close your parentheses, exponent, and you can type it in just like, I mean, it's pretty easy. This is how much is left. So if you are using a scientific calculator, do your 10 parentheses, half. When you do your caret for your exponent on this scientific, you're going to have to put 32 over, you might have to hit divide. I don't remember if they'll let you put a fraction in there or not. You can just do divide by 24,100, but you'll have to put that in parentheses in the scientific. The graphing one will keep it all up as an exponent, so it's okay. How much plutonium started with 10 pounds? It's been 32 years. So give me like to the nearest hundredth. So 9 nearest hundredth, because I think the next digit's a 0, right? Yeah. In 32 years, look how much plutonium still remains. It started with 10 pounds.
Wow. Wait, where's that? Like, that's actual function?
Mm-hmm. Chernobyl.
Oh, yeah.
Mm-hmm. That city is uninhabited because look at, it's been 32 years and there's still almost the same amount of plutonium still in the air. Yeah. Did you? That's awesome. There's wolves that live there? That's weird. It's amazing that they can survive there. They've adapted to it. Oh my gosh. Mm-hmm. That's frightening though, isn't it? That's frightening. But is this a good use of math and using the exponential functions, right? It's a good use of it. That's where it's used all the time. Okay, so there's exponential growth and decay. So this goes back to the question John asked about the graph. So there it is right there for you, John. Exponential growth from left to right goes which direction? It goes up. So exponential growth is this blue line. That one's going up from left to right. The big thing you have to recognize there is that your b value is greater than 1. So the number that's being raised to an exponent, if it's bigger than 1, it's going to be growth. If the b value is between 0 and 1, it's going to be decay. It's going to be going down. Because I'm going to ask you questions like that just by looking at the equation. Is it growth or decay? You just got to look at that b value. If it's bigger than 1, it's growth. If it's between 0 and 1, it's decay. It's going to be positive, though. Why is it what? Because it started out with 10 pounds of plutonium. Wasn't it pounds?
Yeah.
Yes, pounds. So how much plutonium remains? 9.99 pounds. Oh.
Just calculate like how much time based on that it would take for it to
Long time. Long time. And we could. The further we get going in this chapter, we can. We're not to that point yet, though, other than a guessing game. Okay. So identify whether it's growth or decay. So the very first one, my b value is, that's between 0 and 1, so this is going to be decay. So if you would graph this, it would be going this direction, right? From left to right, it'd slope down. And then this one, that's going to be growth because my b value is bigger than 1. That's growth. So your graph's going to look more like that one. From left to right, going up. It is not. Off the top of my head, I don't know its actual, if it has a specific name. I can tell you the x-axis acts as an asymptote. I don't know if you've heard that word before. Because it's like what it approaches but never gets closer to. If you're going to take pre-calc, are you taking pre-calc? No. If you're going to take pre-calc, though, like you talk about a lot asymptotes and stuff in that class. And limits, if you guys ever heard of limits, it talks about all that stuff. Oh, it is useful. It is very useful. Okay. So what we're going to look at next is we can use this basic exponential model, and we can use it, John, in real life to figure things out. It is very useful. Okay? So we, instead of just a times b to some exponent, my b value can kind of vary in there depending on what type of thing I'm looking at. Okay? So for instance, if your parents put $5,000 into a college savings account when you're born, and it pays 5% interest per year, could you figure out how much money is in it after so many years? Yeah, you can. So that's another example. It's exponential, but my b value can kind of change based on what I'm kind of dealing with. And we're going to look at some different formulas. So for the first one here, it's exponential growth and decay still, but my b value, notice, is different. It's 1. I have plus or minus r because it depends on what we're looking at. So the t for my exponent is talking about time in years, or some other time period, typically it's years. A is my initial amount, right? That's the amount of money I'm starting with if I'm talking about money in my savings account. R is your percent increase or decrease expressed as a decimal. So we need to make sure we know how to take a percentage to a decimal. How do you do that? If you don't have the button on your calculator, move your decimal how many spots? 2. So you're going to move decimal 2 spots. Which direction? Left. In other words, what mathematical thing are you doing when you move a decimal 2 spots to the left? Oh, nobody knows? You're dividing by what? You're dividing by 100. That's what you're doing. Dividing by 100 is what's moving it 2 spots to the left. So if I would told you it was 2%, what's 2% as a decimal? 0.02. Good, because you have to move that decimal 2 spots, or divide by 100. Now, depending on whether you use a plus or a minus, you're not using both. I know we're used to seeing that with square roots and stuff. You're either going to add or subtract. I'm going to add if it's growth, right? I'm going to subtract if it's decay or if it's depreciating. Do you guys know what depreciate and appreciate mean? If your investment appreciates, what's it doing? It's growing. If your investment depreciates, it's decreasing. Okay, those words are kind of used. We want to make sure we know what those words mean. Okay, so we're going to have to know this formula. I will give you a formula sheet, so don't panic. You don't have to memorize them. Okay, so my formula, I got it down here for you. You invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest rate. How much will be in the account after 6 years? So all we have to do is use this formula. So y equals the initial amount we had was $1,000. Is it going to be plus or minus? If you put money into an account, you're going to earn interest, right? So it's going to go up. 5% is 0.05. Bless you. And then what's my t value? 6, because after 6 years. Now I want you to recognize this is still in the a times b to the x power formula, right? There's my a, my b is this 1 plus whatever going on in here, and then my exponent is 6. Yes. All right, grab your calculator, type the whole thing in. So how much money is in the account after 6 years? And 10 cents. Don't forget your change. So $1,340.10. So how much interest did you earn? Yeah. See, it pays to put money into a good account, right? Now, a 5% interest rate, is that a pretty standard or is that kind of high? It's kind of high right now for savings accounts. But sometimes, depending on what accounts you can find, CDs, what investments, whatever, you can get some good rates. But yeah. Yeah. It might not be much, depending if it's just a standard savings, it might be pretty small. But still something. All right, the Lorax population is decreasing exponentially at a rate of 13% per year. It is. If the current Lorax population is 101, how many will be left in the year 2020? So we see that this is something that's going up or down, right? So we're going to come to this formula. How many did I start with? My initial amount, 101. And then it's 1, is it plus or minus? Minus, because we're going down. 13% is 0.13. What's my t value? 2, because it's still 2018, right? So it'll be 2 years until it's 2020. All right. So once you plug in your formula, type it in your calculator, how many Lorax will be left? What do you actually get for an answer? You get like 76.4, but if we're talking about a Lorax like an actual thing, so how many will I actually have? It'd be 76. Right, you can have one that's like missing his arms and legs, right? He's just like a little body with a head. Yes.
So, say you have $1 million in savings
Mm-hmm.
That'd be 50 grand. So.
What do you mean a penalty? Nope. And that's what some people do is they invest a lot of money and then they just live off of the interest. So they just, yeah. Yeah. You got to look. Yeah, a lot of people live off, just live off. Yeah, we'll just live off the interest. I don't know where I would find those. All right, take a look at the next one, guys. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by 92% each year. That's a lot. Well, think about 1996 in the computer world, though. But I mean, like, as far as, was that pretty early in computers being, like, mainstreamed and people really getting, it was kind of early into that. So write an exponential growth model giving the number n of incidents t years after 1996. So if I asked you to write a model, are you actually putting the numbers in? No. A model just has variables. Okay? So let's write that first. So I know I'm using this formula because it's exponential growth or decay, right? So it's my formula, but I got to use the right letters that it's asked for. So the number of n of incidents. So which variable is that? Is it y, a, r, or t? The number of incidents. It's y. I'm solving for how many incidents there are, so it's my y. So n equals, can I use the a? Did it tell me a different variable to use for that? It didn't give me. Okay, but do we know the initial amount it was started with? Yeah, we know the initial amount. It started with 2,573. Is it plus or minus? Plus, because it says it was increased, so we're adding to it. Do we know the rate? 92%, which is 0.92. And they want me to use t for years. They want me to use t for years. We're just looking at the model right now. So there's your model. If I asked you 10 years from now, could you just plug in a 10? If I asked you 100 years from now, plug in 100? Okay. So that's a model. Model does not actually have all the parts and pieces filled in. All right. How many incidents were there in 2003? So I'm going to use my model. N equals 2,573. 1 plus 0.92. What's my t value? It is 7. How'd you get 7? Yeah, 9603 is 7 years. Okay, how many incidents were there in 2003? Whew. Was it exact?
It was a 0.71.
Okay, so 247,484, and it was like 0.7. So viruses. So really, I could say that it was 40 or 85. I could round up. I would be okay with that. Now, do you think it continued to climb past 2003 at 92% a year? What do you think happened? Good. I would say the same thing. Just because what happened to our technology to combat the viruses? Do we have like virusware and stuff in our computers to stop all of that? Okay. All right. You're right. It's not necessarily a virus. Yeah. People are good hackers. All right. Now, there's another type of interest. Like we talked about just a regular account, earn an interest, but there's also compound interest. So notice my formula shifted just slightly. So I still have, here's my a times, this is just a number, b to the x, right? It's still the same concept. So p, in this case, starts with my initial principal amount, which is still like the a and the other one. It's just they use a different letter. I still have my r, my rate expressed as a decimal, so I'm going to still put that in here. And then we have n. This is the different part. It is compounded n times per year. So what happens when it's compounded, what that means is they take your initial amount of money, you've earned interest, and then they're going to take your interest and add it on to your principal, and now you're going to earn interest on that amount. So if they said they did it monthly, then every month, if I started with $100, let's say I earned $10 in interest, the next month they're going to take that and say it's $110. And then I'm going to earn interest off of that. So then I might earn $12 in interest that month. So then the next month they're going to add that on. So now it's going off of 122. So every month they keep taking the interest and adding it back on. No. Nope. It's all about how you set up your account. So that's what it means when it's compounded. They're taking that money and putting it back on the principal, so you're earning interest on it. Otherwise, if it's not compounded, and let's say you put $1,000 in, every month from here until you take it out, it's only going to earn interest on $1,000. Whether you have $10 million in that account at that point, it's still on that $1,000 you originally put in. So you want compounded if you're putting money into an account. All right, and then the amount in the account after 2 years, it's the A. It's what you're solving for. So this formula still starts with the amount I'm starting with, my principal. Still 1 plus, but now I'm going to take my rate and divide it by how many times it's being compounded that year. How many times it's being compounded by the number of years. So it just added an extra variable in there. So if it's being compounded monthly, what would your n value be? 12. What if it's yearly? 1. What if it was quarterly? It'd be 4. We see how that works? What about semi-annual? Victoria's Secret semi-annual sale happens how many times? Twice. It's twice. Semi-annuals, 2. N is the number of times it's compounded per year. And then you multiply by t, which is the time. So let's take a look at some examples of it. You multiply n times t. N, t. Multiply them. All right, so if $12,000 is invested in an annual interest rate of 9%, find the balance after 5 years if it is compounded quarterly. Now, it always comes up, students like, well, how do I know which formula to use? The one we were just using or this one? If it says the words compounded, you use the compounded formula. Makes sense, right? You can kind of look for that word in the description. So, using that formula, so A equals, what is my P, my principal? 12,000. That's how much I'm starting with. 1 plus 9% is written as 0.09 divided by n. How many times is it being compounded if it's quarterly? That is 4. Think of 4 quarters in a dollar, right? And then my exponent is nt. That means it's 4 times, how many years? 5. Now, if you are using the scientific calculator, again, your exponent would have to be in parentheses 4 times 5. Okay? So go ahead and practice this on the calculator, guys. Don't let the calculator be your issue on these. Can somebody tell me how much money would I have? How much? I heard holy crap. So if I'm talking money, I need 2 decimal spots. 11 cents. Check your calculator. If you did not get that, so yeah, make sure you close the parenthesis after. Yeah, if you don't close parenthesis after a fraction, you're going to get a very different answer. Monty, did you put your 4 times 5 in parentheses? Yeah, see, since you're on that calculator, after you hit your caret, you're going to have to open a parenthesis, 4 times 5, and then close them like that. Yeah, otherwise, your calculator raised it to the 4th power, and then took that answer and multiplied it by 5. Yeah, order of operations. That's why I like the graphing ones, because it keeps your exponent up there so it stays all up as an exponent. If you put your fraction in parentheses, yeah. Now, real quick, guys, on the calculators, just to maybe save you some time, do you have to type this as an actual fraction, or can you just hit divide? You can just hit divide, and John, you would not need parentheses around that. So you could just do 12,000 parenthesis 1 plus 0.09, type in the divided by 4, close that one, and then make your exponent. And then if you're on the scientific, that would have to be in parentheses. If you're on graphing, it doesn't have to be. But order of operations is going to divide that first before it adds the 1, so you wouldn't technically have to put an extra parenthesis or put it as a fraction. Okay, anyone not able to get that to work?
If you put $100,000
In interest? Isn't that nice? All right, how much would this same investment yield if it were compounded monthly? So if it's done monthly, let's set this up. It's still 12,000 I'm starting with. 1 plus, still the same rate, 0.09. If it's monthly, what's my end value? 12. So then my exponent is going to be 12 times 5. So instead of it compounding just 4 times a year, what if it did it 12 times in a year? Should you make more or less? You think yeah, it'd be more. How much more would it be? So what would I be? So not a huge difference, but is it still more? Still more. Hey, I'll take more money. Now, if this kind of thing really interests you, like you're like learning stuff like this, the FST or financial algebra class that's offered for seniors, that we do a whole chapter on stuff like this. And talk about different types of savings accounts and how to like grow your money and stuff like that. So if you really like this kind of stuff, then that financial class would be awesome. All right, what if you deposit $4,000 in an account that pays 2.92% annual interest? Find the balance after 1 year if the interest is compounded with a given frequency. So there's 2 different options. All right, now how do you know which formula to use? It says compounded right here. Right? If it says compounded, use the compounded formula. So it's going to be A equals, I started with $4,000. 1 plus, what's my rate? What would that be? It'd be point what? $0.0292. Now, if it's quarterly, what's the end value? It is 4. And then 4 times, it wants just 1 year, so 1. So how much do I have after a year? It's compounded quarterly. Not, right, I don't want the interest. How much money? There he goes. $4,118, any change? And 9 cents. Yeah, guys, keep in mind with your decimals, we're talking money. So we want 2 decimals for change. So I earned $118 just by leaving my money sit in that account for the year. All right, what if it was compounded daily? So 4,000, parenthesis, 1 plus, same interest, 0.0292. What's the end value? 365, good. And 365 times 1. I should make more, right? It's compounded more often. How much money do I have now? Anyone? Bueller? How much do I have? Now that was in a year. Do you think as time goes on, if I let that go for many years, it'll add up a little more? Yes? No? Yeah, probably. Now what's the difference between this one, where I only earned a few cents more, versus the other one I earned actually dollars more? What's the differences? The interest rate. The interest rate was a lot higher on the other one, and the other one was for a longer amount of time. Okay, this is just 1 year at a really low interest rate. The other one was like for what, 4 or 5 years, and it was a higher interest rate. It's gonna make a difference.
So wait a minute.
Yeah.
Why is it a dollar payout, 2.92? Wouldn't that make
0.0292, so 2.92%. That's a lower percentage versus if I had like 5% interest rate or 9%. They're going to pay you more. This is lower. Because the initial percent is 2. So 2.92 is like almost 3% versus like 9% on that one. You got to look at the initial percent, not necessarily the decimal end of it. Right, so it's close to 3%. Yeah. Now, is that going to make more than 2%? Yeah, 2.92 is more than, yeah, but it's not a whole lot more. All right, so guys, we are going to kind of shift gears slightly. All right, we're shifting gears just a little bit. I apologize, your notes I noticed after the fact did not print, like it didn't print Linus and it didn't print this. So I don't know exactly what happened. Go ahead and fill in your table. Sorry, take a second, fill in that table. I printed off the X, but that was like all it printed. Quickly. Yeah, so go ahead and fill in the rest of that table. Sorry, and it didn't even print Linus, which is weird. Yeah, it's the table, whatever reason, when it updated, the tables don't print anymore other than the first cell. I went through a lot of them and fixed those, but apparently I missed that one.
Yeah, it's really low. I have to know the whole thing is
All right, so we're looking at something slightly different. Again, it's the same idea of we're still working on our basic exponential functions. In this case, what's my a value? What's the a value right here? It's a 1, right? This is my b. It's going to be some number to an exponent. So I'm still dealing with that same a times b to the x, right? My formulas just look slightly different, okay? So let's kind of look and see what's happening here. So if I plug in a 1 for x, so that means the 1 goes here and the 1 goes here. Really? This would be 1 plus 1 to the first. It'd be 2. Okay. So what happens if I plug in a 10? That one you're going to actually, again, just type it straight in your calculator. Don't guess. Type it in your calculator. What'd you say again? Okay. So 2.5 some. It's still got the 2 out in front though, right? What if I put in 100? Does it still end up 2 something? Yeah? $2.705. But it's still got the 2. You think it's always going to be there? What happens if I put in 1,000? What's the decimal? 2.717, around that. All right, so okay, now it's stuck at 2.7 something. What if I put in 10,000? 2.718, you said? So now it's a 2.71. What if I put in 100,000? 2.718 again. But the number really doesn't get bigger though, right? It's still 2 point something. So what the heck did we just find? The natural base E. Look on your calculator. On the graphing one, there, right next to the 4, there's a button that says LN. Look above it. It has a little e with an x for an exponent. Right? LN stands for natural log. We'll get into that later this week. But right above it, e to the x. E is a number. Just like pi. What's pi? Right? Like you guys can rattle off some decimals of pi, right? It's an irrational number that we use a symbol to represent it, right? So is e. E is approximately this number. So e stands for a number just like pi does. Okay? As x approaches positive, what's that symbol? Infinity. Means as numbers get bigger and bigger and bigger and bigger and bigger, right? We started off with a 1, a 10, 100. Like we got those numbers bigger and bigger. That was the formula we dealt with. It approaches this number. So we call that e. So just like pi is a number, e is a number. Okay? So how do we, I don't want to skip this. The fact that there's decimals, we don't really care. We use that for another formula. And again, investing money is a big thing that we look at. APERT. That's what I always call this formula, APERT. A is the amount of money after t years. So we're still solving for money. P is still my principal. E stands for a number, right? We have an E button on our calculator. And then the R is still my interest as a decimal. It's still the same letters and formula. But this formula is used when it is continuously compounded. It's always taking it constantly and rolling that money over. So that is where that letter E, it's one of the reasons it's actually used. So how will you know to use this formula? It will say continuously compounded. Okay? You'll have to figure out which formula it is. If it doesn't say compounded anywhere in it, you use the first one we talked about. If it says compounded quarterly, monthly, yearly, whatever, you use the compounded formula. And if it says it's continuously compounded, you use this one. So there's very key words in there. Yeah, you'll know by reading it. All right, so let's take a look at this formula. So if you deposit $2,500 in an account that pays 5% annual interest compounded, thank you, compounded continuously. So that's going to tell you which formula to use. So for part A, it's A equals the p-value. It's my principal. I started with 2,500. And then we have an E. That is not a variable. E is a number, not a variable. To the RT power. My rate, what's 5%? 0.05. And my time, this was 2 years. So you're going to grab your calculator. We'll type in 2,500. And then, at least on the graphing, I have to look at the scientific. It's second and then the LN button. Double check your calculator, scientific people. I don't have one of those in front of me. Like on the graphing one, it actually brought the E, and then it popped it right up to the exponent. ln is right next to the 4. Scientific people, did you find it? It still is ln. Okay, still second ln. Did it open up a little caret? Did it open a parenthesis? Perfect. And then your exponent is 0.05 times 2. $62.93. Round that to the nearest cent. Anyone not able to figure out the calculator? Okay. So if I do this for 5 years. So same idea. 2,500 E. My rate is still 0.05, and my time now is 5. Yeah, so if you're good with the calculator, just bring up that same equation again, arrow back over, and change the 2 to a 5. That's what I would do. Heard somebody whispering it over there. $3,210.06. And then to do it for 7.5 years. And again, if you're good at the calculator, just arrow back up, change that to 7.5. $3,637.48. Watch your cents. If you round your change incorrectly, I'm counting it wrong. You are juniors and seniors in high school. You should know how to round to the nearest cent at this point. Okay? That's right. 400, it stays down. All right. So are we okay with the E and how to use that in the calculator? E is a variable or a number? It is a number. It stands for 2.71 something, blah, 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 right? It's not a variable. Variable means that I could put anything in for what I want. No, E is a number. Watch your mouth. All right. So from this section, I want to kind of let's talk back through the formulas we talked about, okay? So we started with an exponential function, right? Very basic function. Do I ever actually just plug numbers directly into this equation? And any of the story problems we did I go back to this specific one? No. So do not plug numbers in here. So do not plug numbers in here. That is your basic formula. Now, what do we know about all the formulas we've been using? They're all set in this form. They're all set up A times B to the X, right? On this one, here's your A times B to the X. Like, it's got all the same pieces. They're all exponential. This is just the basic one. How do you know to use compound interest? How do I know to use this formula? It will say it's compounded yearly, monthly, whatever. So if you actually see the word compound, you use this one. How do I know whether to use this one? It'll just say it's been increased or decreased. It will not use the term compound anywhere in it. Okay? This will say like increase or decrease. That tells me whether to use the plus or the minus, whether it's increase or decrease. Okay? And continuously compounded, how do I know to use that one? It will say continuously compounded. So should you have trouble knowing which formula to use? You should not. Look at the wording in the problem. Okay?